More than half of the living space on Earth lies beneath the ocean's surface, yet humans have explored far less of this environment than the surface of the moon. A few hundred meters below the waves, sunlight fades rapidly. By roughly 200 meters, most light has disappeared entirely. What remains below is a vast region of permanent darkness stretching for thousands of meters. Temperatures hover near freezing. Pressure rises so intensely that most surface animals would be crushed almost instantly. And still, life thrives there. Many deep-sea animals may drift through this darkness for weeks or even months without encountering another living creature. Food is scarce, often arriving only as small particles slowly sinking from the distant world above. Encounters are rare, but when two animals finally meet, hesitation can carry a cost few creatures can afford. Scientists studying deep-sea predators repeatedly discover prey almost as large as the hunter itself. Some fish have been found with stomachs ruptured after swallowing animals too large to digest. Others have been recovered with prey still lodged halfway down their throats. In this environment, an opportunity to eat may not return for weeks. Many predators have evolved enormous mouths, expandable stomachs, and teeth that appear oversized for their bodies. Some strike at anything that moves. Others rely on small lights to lure prey close enough to seize. Cameras lowered into the depths sometimes record moments that last only seconds. A shape appears from darkness, a sudden movement follows, and then everything returns to stillness again. But the calm appearance of the deep ocean hides a different pattern. Encounters may be rare, yet they often end in violent struggles where both animals risk everything for a single meal. In this video, we descend into the deep sea to explore why the deep sea has become one of the most intense hunting environments on Earth. Now, let's begin. Far below the restless surface of the ocean, depth becomes less a distance and more a gradual surrender of light. Water thickens into layers where brightness weakens with every meter, like a slow dimming of the world above. The boundary that scientists often mark as the beginning of the deep sea lies near 200 meters, a depth where sunlight loses its strength and colors begin to vanish. Reds fade first, then oranges and yellows, until the remaining light narrows into a cold blue haze. From this point downward, the ocean shifts into a realm shaped not by daylight, but by shadow. Marine researchers often describe the next region as the twilight zone. Here a faint glow still filters down from distant skies, though it arrives scattered and weakened after passing through hundreds of meters of water. Shapes remain visible only as silhouettes, and movements become ghost-like against the dim background. Animals living in this band rarely rely on clear sight alone. Eyes grow large and sensitive, tuned to capture the smallest fragments of light. Many species rise and fall through this layer each day, drifting upward at night and sinking again before morning, part of a slow migration that quietly reshapes the ocean every evening. The descent continues until even the diluted glow disappears entirely. Below roughly 1,000 meters begins the midnight zone, a vast expanse where sunlight never arrives at all. Darkness here is not the gentle dimness of night on land, but a complete absence, an environment where the concept of day has no meaning. Vision changes purpose in such conditions. Some animals retain enormous eyes to detect the faint flashes produced by other organisms, while others abandon sight almost entirely. Bodies become soft and flexible, conserving precious energy while drifting through water that remains close to freezing. In these depths, light behaves as a fragile traveler that cannot journey far. Each meter of water absorbs another fraction of its energy, scattering the remaining rays until they dissolve into blackness. The process unfolds gradually rather than suddenly, creating a layered ocean where brightness fades step by step. Near the upper boundary, there is still enough illumination for shadows to exist. Deeper down, contrast disappears, and the surroundings merge into a single dark field. Movement becomes difficult to perceive unless something produces its own glow. Darkness reshapes behavior in subtle ways. Animals cannot depend on distant visibility to locate prey or avoid danger, so many drift slowly, conserving strength while listening for disturbances in the water. Senses tuned to vibration, scent, and faint light become more valuable than speed. A predator may travel long distances without crossing the path of another creature. At times, the ocean around it remains empty in every direction, a quiet volume of water stretching far beyond the reach of its senses. Yet this immense emptiness produces a strange consequence. When two animals finally enter the same patch of water, the meeting carries unusual weight. There are few opportunities in a place where food drifts sparsely and movement costs energy. A shadow detected too late may already be closing in. A faint glimmer might signal the difference between nourishment and another long interval of waiting. In the deep sea, darkness spreads life thinly across enormous distances, but the rare crossings of those scattered lives can unfold with sudden, decisive intensity. In the open ocean far below the reach of coastal nutrients, energy arrives only in fragments. Life here cannot depend on fields of algae or drifting clouds of plankton. Instead, nourishment descends slowly from the distant surface, carried downward through thousands of meters of water. The deep sea exists at the far end of a long journey that begins in sunlit waters and ends in quiet darkness, where every trace of organic matter becomes valuable. Much of this energy arrives in a form known as marine snow. The name suggests something delicate, and the comparison is not far from the truth. Countless tiny particles drift downward through the water column, settling gradually toward the sea floor. These fragments include microscopic remains of plankton, grains of waste, shed skin, broken shells, and countless other pieces of once living material. From a distance, the descent resembles a slow underwater snowfall, a steady rain of organic debris falling from a world far above. For animals living in the depths, this drifting material forms the base of an extremely thin food supply. Small crustaceans, worms, and other scavengers gather what they can from the gentle fall. Each particle contains a trace of energy captured long ago by sunlight at the surface. By the time it reaches great depths, much of that energy has already been consumed along the way. What remains is sparse and widely scattered. Because of this scarcity, many deep-sea organisms survive on remarkably small amounts of food. Their bodies often grow slowly, their movements measured and careful. Metabolism operates at a quiet pace that allows life to continue, even when meals arrive only occasionally. The ocean in these depths feels vast, not only in size, but also in time. Days and weeks may pass with little change, except for the steady descent of faint organic dust. At rare moments, however, the deep sea receives something far larger than drifting particles. When a whale dies near the surface and its body begins the long fall to the sea floor, the event transforms the surrounding ecosystem. The immense weight of the animal sinks through the water column until it settles on the seabed, carrying with it a store of nutrients far greater than anything normally available at such depths. These fallen giants create temporary islands of abundance. Scavenging fish arrive first, followed by crabs, worms, and specialized organisms that can break down bone and connective tissue. Over time, entire communities gather around the remains. The whale's tissues feed animals for months, sometimes even years, as microbes and scavengers gradually dismantle the body. What began as a single life drifting through the upper ocean becomes a long-lasting source of energy for creatures living far below. Yet such events remain rare across the enormous expanse of the deep ocean. Most of the time, animals continue to exist in a landscape defined by shortage rather than plenty. Food arrives unpredictably, often in quantities too small to sustain leisurely feeding. Survival depends on making the most of each opportunity that appears. This persistent lack of energy quietly shapes the behavior of predators. In environments where meals are uncertain, hesitation becomes costly. When a moving shape enters reach, the moment may represent the only chance to feed for many days. The logic of survival encourages decisive action, even when the size or identity of the target remains uncertain. Over countless generations, this pressure has guided the evolution of feeding strategies that appear extreme when viewed from the surface world. Predators become willing to attempt meals that seem disproportionate to their own bodies. Opportunistic attacks replace careful selection. The deep sea does not reward restraint. It favors creatures prepared to seize energy whenever it passes within reach. Within this immense and sparsely nourished realm, each fragment of organic matter carries importance. From drifting specks of marine snow to the sudden arrival of a whale fall, energy flows downward in fragile threads. Life persists by following those threads patiently through the darkness, where even the smallest opportunity may shape the rhythm of survival. Across the immense distances of the deep ocean, living creatures often move through water that holds little sign of other life. A fish may glide forward through the dark for long stretches of time, with nothing but faint currents brushing past its body. The surrounding space remains wide and quiet, filled mostly with drifting particles and the occasional tremor carried through the water. Life exists here, yet it is scattered so thinly that one animal can travel far before crossing the path of another. Because of this separation, meetings between creatures become uncommon events. Two animals approaching the same volume of water have likely followed different currents, different trails of scent, or subtle changes in pressure that guided them from distant places. Their arrival in the same small region may last only moments before each drifts onward again. For a brief instant, two separate journeys intersect within the vastness. In such conditions, hesitation carries consequences. A predator that pauses too long may lose the only meal it encounters for many days. Prey animals also move with urgency, their senses tuned to the smallest disturbance. The water itself transmits information through faint vibrations, allowing nearby creatures to perceive movement before shapes become visible. Even in darkness, presence reveals itself through subtle shifts in pressure and motion. As these signals travel outward, animals respond quickly. A slight tremor may cause a hunter to turn sharply toward its source. A passing body might release traces of scent that drift slowly through the surrounding water. The deep sea rewards creatures that react without delay, because opportunities appear rarely and disappear just as quickly. Over long spans of evolutionary time, this pattern has shaped a style of feeding that favors decisiveness. Many predators no longer rely on careful inspection of potential prey. Instead, they strike whenever something living moves within reach. The distinction between familiar food and unknown animal becomes less important than the chance to capture energy before it escapes. This opportunistic approach appears in the design of many deep-sea predators. Jaws open wide with sudden force, teeth angled inward to prevent escape once contact is made. A passing animal may trigger an immediate attack even if it is nearly the same size as the hunter itself. The cost of ignoring a possible meal often outweighs the risk of attempting one that proves difficult to swallow. Some encounters unfold with remarkable speed, a predator drifting almost motionless, may detect a faint disturbance approaching through the water. In an instant, its body shifts from stillness to motion, lunging forward with jaws already open. The entire event can conclude within seconds, leaving little trace in the surrounding darkness. Water settles again, and the space returns to its quiet state. Other meetings develop more gradually. Two animals sense one another at a distance and begin subtle adjustments in movement. A hunter might circle slowly, maintaining position until the right moment arrives. Meanwhile, the potential prey attempts to slip away through the surrounding water, guided by the faint signals of approaching danger. Even these brief interactions remain shaped by urgency, since neither creature can afford prolonged effort in a world where energy is difficult to replace. Occasionally, the outcome reveals the limits of this relentless strategy. Predators, driven by scarcity, sometimes attempt to swallow prey that challenges their own physical capacity. Bodies stretch, jaws strain, and the effort can leave both animals locked together in an uneasy struggle. Such scenes rarely last long, yet they illustrate how strongly the environment favors decisive action. Within the deep sea's immense and quiet spaces, encounters remain fleeting and unpredictable. Creatures travel alone for long intervals, guided by subtle cues carried through the water. When two paths finally cross, the moment carries unusual significance. The meeting may pass without contact, or it may resolve quickly in an attempt to seize the fragile energy that sustains life in the depths. Certain predators of the deep ocean appear built around a single purpose. Their bodies may be modest in size, yet their mouths dominate their form, lined with teeth that seem disproportionate to the rest of their anatomy. The impression is not one of elegance, but of capability, as if evolution gradually rearranged bone and muscle to prioritize the act of seizing prey whenever the opportunity appears. In the sparse world of the deep sea, such proportions are not accidental. Over long periods of time, animals that could grasp and secure food more effectively were more likely to survive. Even a small advantage in capturing prey could shape the design of future generations. Gradually, jaws lengthened, teeth thickened, and skulls adapted to allow wider openings. Many deep-sea predators possess teeth that curve sharply inward. This shape reduces the chance that struggling prey can escape once caught. The teeth often remain visible even when the mouth is closed, forming a cage of pointed structures that guide captured animals deeper toward the throat. These features function less as tools for cutting and more as hooks that hold prey firmly in place. The skull itself often shows unusual flexibility. In surface animals, the bones of the head may connect tightly, limiting how wide the mouth can open. Deep-sea hunters frequently display a different arrangement. Their skull bones can shift slightly against one another, allowing the jaws to expand outward when something large enters the mouth. Ligaments stretch, joints rotate, and the opening grows far wider than the animal's resting shape might suggest. This flexibility extends beyond the jaws. The body cavity of many species can expand significantly after feeding. Their stomach walls contain elastic tissues capable of stretching around a meal that may rival the predator's own size. After swallowing such prey, the body slowly adapts to accommodate the sudden intake of energy. Digestion may take many days, sometimes even longer, as enzymes gradually break down the captured animal. Such adaptations reflect a strategy shaped by scarcity. In environments where meals appear unpredictably, animals cannot afford to be selective. The ability to consume a large prey item in a single encounter may provide enough energy to sustain life through extended periods of drifting and waiting. An animal that rejects an available meal because it appears inconvenient may not encounter another opportunity for a very long time. Over generations, this pressure encouraged a pattern that might be described simply as immediate consumption, followed by later resolution. When movement appears nearby, the safest approach often becomes to capture first and evaluate afterward. If the prey proves manageable, the predator gains valuable energy. If the meal stretches the limits of digestion, the body still attempts to process what it can. In some cases, the results reveal the extreme nature of this evolutionary gamble. Researchers examining recovered specimens occasionally discover prey lodged deep within the throat or stomach, nearly matching the predator's own mass. These findings illustrate how strongly the deep sea environment rewards the attempt to secure any available nourishment. Despite their formidable appearance, many of these predators move slowly through the water, conserving energy between rare encounters. Their oversized teeth and flexible jaws remain ready for the moment when another animal passes close enough to grasp. The entire body becomes an instrument prepared for a brief but decisive act. Within the quiet depths of the ocean, where resources drift thinly across enormous distances, such adaptations provide a practical advantage. Large teeth hold struggling prey, mobile skull bones widen the mouth, and expandable stomachs store the reward of a successful capture. Together, these features form a design that reflects the patient but relentless logic of survival in a place where every meal carries lasting importance. Among the many hunters that inhabit the deep ocean, one species carries its own small light into the darkness. At the front of its head rises a thin extension of the dorsal spine, arching forward like a delicate fishing rod. Suspended at the tip rests a soft bulb that glows with a steady radiance. This structure, known as an esca, contains colonies of bioluminescent bacteria that produce light through a gentle chemical reaction. In the surrounding black water, that glow becomes a point of quiet attention. The animal that bears this luminous lure is the anglerfish. Its body often remains compact and still, hovering just above the seafloor or drifting slowly through midwater. Muscles remain relaxed, fins barely moving, as the fish maintains a posture that conserves energy. Only the small light at the tip of the esca moves, swaying gradually in the water like a drifting speck of life. For smaller animals traveling through the depths, the glow may resemble the movement of something edible. Tiny crustaceans, curious fish, and other wandering creatures sometimes draw closer, guided by instinct toward what appears to be a source of nourishment. The anglerfish does not pursue them. It simply waits while the light performs its quiet invitation. The stillness of the hunter hides an anatomy designed for sudden action. Its head forms a large portion of the body, with jaws capable of opening at remarkable angles. Rows of long, slender teeth extend inward, each angled to prevent escape once something slips between them. The mouth remains slightly open even while the fish rests, ready to expand in an instant. As prey approaches the glow, the anglerfish adjusts the movement of the esca with subtle motions. The lure may twitch gently or drift in a slow arc, mimicking the behavior of a small animal suspended in the water. These movements remain delicate, almost effortless, allowing the hunter to continue conserving energy while maintaining the illusion of vulnerable prey. When the distance becomes small enough, the entire encounter shifts in a fraction of a second. Muscles along the jaw and throat contract rapidly, forcing the mouth to expand outward. The water surrounding the prey rushes inward as the jaws open, creating a sudden flow that draws the nearby animal directly toward the throat. This method, often described as suction feeding, allows the anglerfish to capture prey without needing to chase it through the water. The speed of this action is remarkable. High-speed recordings from deep-sea cameras reveal that the strike can unfold in less than a tenth of a second. One moment, the lure glows quietly in the dark water. In the next instant, the prey disappears into the widening mouth, and the jaws close again with calm precision. After the capture, the anglerfish resumes its still posture. The luminous esca continues to glow softly above the head, returning to its slow drifting motion. The surrounding water settles once more, carrying only faint traces of the brief movement that just occurred. This method of hunting reflects the quiet economy of the deep ocean. Rather than expending energy in long pursuits, the anglerfish allows the environment to deliver prey within reach. The glowing lure functions as both signal and trap, drawing curious animals toward a hunter that barely moves. Through this strategy, the anglerfish transforms a small point of light into a powerful advantage. The glow travels farther through dark water than scent or motion alone, guiding wandering creatures toward the waiting jaws. In the stillness of the depths, the ambush unfolds with quiet efficiency, one of the fastest feeding events known in the deep sea. A faint glimmer sometimes appears in the deep ocean that most creatures nearby cannot perceive. The water remains dark to their eyes, empty and undisturbed, yet a narrow beam of crimson light passes silently through the surrounding space. Within that invisible illumination moves one of the deep sea's most specialized hunters, the dragonfish. Dragonfish belong to a group of predators that carry bioluminescent organs along their bodies. Many deep-sea animals produce blue or green light, colors that travel efficiently through seawater. The dragonfish possesses something far more unusual. Beneath its eyes sit small photophores capable of emitting a dim red glow. In the deep ocean, this wavelength behaves differently, fading quickly and remaining undetectable to most animals that live in darkness. The secret of this ability lies not only in producing the light, but also in perceiving it. Dragonfish eyes contain specialized pigments that allow them to detect red wavelengths that surrounding species cannot see. To most creatures in the depths, red light effectively disappears, absorbed by water before it travels far. For the dragonfish, however, this glow becomes a private lantern carried through the blackness. When the fish activates these photophores, a soft crimson beam spreads outward like the narrow cone of a flashlight. The surrounding water remains silent and still, yet within that small field, the dragonfish gains the ability to observe nearby shapes. Tiny crustaceans drifting in the current, slender fish gliding through mid-water, and other small animals briefly enter the range of its hidden illumination. Because the prey cannot detect this wavelength, the hunter approaches unnoticed. Many deep-sea species evolved eyes tuned to the blue spectrum, the color most commonly produced by bioluminescent organisms. Red remains beyond their perception. The dragonfish moves through water that appears completely dark to its prey, while its own vision quietly reveals what lies ahead. The body of the dragonfish reflects the demands of this secretive method of hunting. It remains slender and elongated, allowing the fish to glide slowly through the water with minimal disturbance. Long teeth extend from the jaws like thin glass needles, translucent and sharp. These teeth curve inward slightly, guiding captured prey toward the throat once the mouth closes. Along the underside of the body, additional photophores create faint patterns of blue light. These organs serve different functions, sometimes helping the fish blend into the faint glow filtering from distant waters above. Yet the red light beneath the eyes remains its most unusual adaptation, transforming the predator into an observer moving through a darkness that conceals its presence. When prey drifts within reach, the dragonfish closes the remaining distance with a brief acceleration. The jaws open, revealing rows of narrow teeth that form an effective cage. The strike remains swift but controlled, requiring little movement beyond the sudden extension of the mouth. Within moments, the prey disappears between the slender jaws, and the surrounding water returns to stillness. Afterward, the crimson beam fades again. The dragonfish continues its slow passage through the deep, carrying within its eyes a spectrum that few other creatures share. The ocean around it appears silent and empty to most inhabitants. Yet the predator travels with a subtle advantage, able to examine the darkness while remaining hidden within it. Through this remarkable combination of vision and light, the dragonfish occupies a quiet niche in the deep-sea ecosystem. Its strategy depends not on speed or strength alone, but on the ability to observe without being observed. In the immense darkness of the ocean depths, a narrow glow of unseen red light becomes a private window through which a patient hunter searches for passing life. In the deep ocean, there exists a creature whose proportions appear almost unreal when first observed. Its body stretches long and slender through the water, dark and ribbon-like, yet the head opens into a vast, circular mouth that seems far too large for the rest of its form. This animal, known as the gulper eel, carries a feeding apparatus that dominates nearly its entire anatomy. The mouth alone can reach a size that rivals the eel's own body length. When closed, the edges fold inward like the loose fabric of a net. The skin surrounding the jaws remains thin and highly elastic, allowing the mouth to expand outward into an enormous pouch. Rather than relying on rigid bone, the structure depends on flexible tissue and elongated jaw elements that stretch wide when pressure from captured prey pushes against them. As the eel drifts through the depths, its movements remain slow and deliberate. The body tapers into a long tail that often ends with a faintly glowing organ, a small source of bioluminescent light that may help attract curious animals in the surrounding water. The eel rarely chases prey over long distances. Instead, it glides patiently, allowing the environment to carry potential meals within reach. When an animal approaches close enough, the gulper eel begins its feeding sequence. The jaws swing open with surprising breadth, forming a wide oval that suddenly reshapes the front half of the body. The mouth expands forward while the surrounding skin stretches outward, creating a flexible chamber that can envelop large volumes of water. Inside this expanding pouch waits a series of small but sharply pointed teeth. They are not built to slice prey apart. Their function is simpler and more effective. Once an animal slips inside the mouth, the teeth angle inward, preventing escape while the eel closes its jaws around the captured body. The scale of the mouth allows the gulper eel to attempt meals that would seem impossible for many other fish. Prey approaching the eel's own length may still be drawn into the expanding pouch. As the jaws close, the flexible throat begins the process of guiding the captured animal deeper toward the stomach. Digestion requires additional adaptations. The stomach of the gulper eel stretches dramatically after feeding, expanding to accommodate prey that may nearly match the predator's own mass. The body walls remain thin yet resilient, capable of enlarging without tearing as the meal settles within the abdomen. This capacity allows the eel to store significant energy from a single successful encounter. Such an extreme feeding strategy reflects the conditions of the environment where the gulper eel lives. In a realm where opportunities arrive unpredictably, the ability to consume large prey provides an important advantage. One substantial meal can sustain the animal through extended intervals of quiet drifting, reducing the need for constant hunting activity. Observations from deep-sea expeditions occasionally reveal gulper eels with their stomachs distended to remarkable proportions. The outline of the swallowed prey sometimes remains visible through the thin outer tissue of the abdomen, forming a temporary bulge that slowly diminishes as digestion progresses. Despite the dramatic design of its mouth, the gulper eel remains a patient hunter rather than an aggressive pursuer. Much of its life passes in measured movement through dark water, conserving energy while the environment slowly delivers possibilities. The enormous jaws wait quietly at the front of the slender body, ready to transform from folded membrane into a wide capture net at the precise moment when prey drifts close. Through this unusual structure, the gulper eel demonstrates how deeply the conditions of the deep ocean shape the bodies of its inhabitants. Flexibility replaces rigidity, expansion replaces restraint, and a single remarkable mouth becomes the central tool that allows the animal to endure in a world where each successful capture may determine survival for many days to come. In certain regions of the deep ocean, a small predator drifts through the water with a face that appears almost exaggerated in its proportions. The body remains compact and muscular, yet the mouth carries teeth so large that they define the entire silhouette of the animal. This fish, known as the Fangtooth, possesses one of the most striking dental structures found in the deep sea. Despite its intimidating appearance, the fangtooth rarely grows longer than the span of a human hand. Its size remains modest compared with many other predators that share the same depths. What sets it apart is the extraordinary scale of its teeth, particularly the two large fangs that extend downward from the upper jaw. These teeth are so long that the lower jaw alone cannot fully contain them when the mouth closes. To accommodate this unusual anatomy, the skull of the fangtooth has evolved a distinctive solution. On the roof of the mouth lie small hollow pockets that receive the tips of the upper fangs whenever the jaws shut together. When the mouth closes, each tooth slides neatly into its corresponding cavity, allowing the predator to seal its bite without piercing its own tissue. This arrangement forms a precise alignment between teeth and skull, maintaining both safety and efficiency during feeding. The rest of the jaw contains numerous smaller teeth arranged in tight rows. These structures angle inward slightly, creating a surface designed to hold prey securely once captured. Unlike slicing teeth that cut through flesh, these fangs function more like hooks, ensuring that struggling animals remain trapped within the closing jaws. The fangtooth inhabits depths where sunlight never arrives, often between 500 and 5,000 meters below the ocean surface. In these remote layers of water, the fish moves steadily through the darkness, guided by sensitive eyes that detect faint glimmers produced by other organisms. Its body remains well suited for this environment, compact enough to conserve energy yet strong enough to deliver sudden bursts of motion. When prey appears nearby, the fangtooth acts with swift precision. The jaws open wide, revealing the long upper fangs poised like curved spears. A short forward movement brings the predator close enough for the teeth to engage. Once contact occurs, the inward pointing arrangement prevents the captured animal from slipping free. The design of the fangtooth emphasizes reliability rather than complexity. Every feature of the mouth supports the single task of seizing prey and holding it firmly until swallowing becomes possible. The oversized fangs increase the chance that any contact between predator and prey results in a secure grip. Even animals that approach from awkward angles may find themselves caught by the long teeth before they can escape. Scientists examining fangtooth specimens have noted that the fish often consumes animals nearly its own size. The jaw structure allows the mouth to open widely, while the throat expands enough to guide relatively large prey into the digestive system. This capability proves valuable in an environment where encounters with food remain unpredictable. Although its appearance suggests constant aggression, the fangtooth spends much of its time drifting quietly through the water. Movement remains controlled and efficient, conserving energy between feeding opportunities. The large teeth remain exposed even when the mouth rests in a closed position, forming a permanent outline that gives the species its name. Within the quiet depths where the fangtooth lives, such anatomical features represent the outcome of long evolutionary refinement. The enlarged fangs, the skull cavities that receive them, and the inward-pointing rows of smaller teeth all contribute to a single function. The predator does not rely on speed or elaborate hunting displays. Instead, it carries a mouth shaped entirely for the moment when prey passes close enough to grasp, turning a brief encounter into a successful capture. Seen from the side, the hatchet fish appears thin as a blade of metal, its body compressed into a narrow shape that reflects faint glimmers of distant light. The profile resembles the edge of a small hatchet, which is how the animal received its name. Yet, its unusual form serves a deeper purpose. Every curve of its body helps it vanish within the dim layers of water where it spends its life. Hatchetfish inhabit depths where traces of light still filter down from far above. In this region, the water never becomes fully bright, yet it is not entirely dark either. Instead, the environment holds a pale glow that spreads downward through the ocean like a distant haze. To animals swimming below, any creature silhouetted against this faint brightness can appear as a dark outline. Predators moving upward through the water often search for such silhouettes. A fish drifting above them may reveal its shape simply by blocking the dim illumination that descends from the surface. Even a small body can stand out against the faint glow if its underside remains dark. The hatchetfish has evolved a remarkable solution to this challenge. Along the underside of its body lie rows of small organs known as photophores. These structures produce bioluminescent light through chemical reactions occurring inside specialized cells. Instead of shining brightly, the photophores emit a soft glow that spreads gently across the belly of the fish. This light performs a precise function. The brightness from the photophores closely matches the faint illumination filtering down from above. When viewed from below, the glowing underside of the hatchetfish blends seamlessly with the background light. Rather than appearing as a dark shape against the surface glow, the fish becomes almost indistinguishable from the surrounding water. This strategy is known as counter-illumination. By producing its own light, the hatchetfish cancels out the shadow that would normally reveal its presence. Predators, searching upward through the water, encounter only the same dim brightness they expect from the distant surface. Achieving this balance requires constant adjustment. The intensity of the light above changes gradually depending on depth, time of day, and the clarity of the water. Hatchetfish possess sensitive eyes that face upward, allowing them to monitor the brightness of the environment above them. Using this information, the fish can subtly modify the glow produced by its photophores. If the surrounding light grows slightly stronger, the photophores brighten to match it. If the glow above fades, the fish dims its own light accordingly. This delicate calibration allows the animal to maintain its camouflage while drifting through varying conditions. The rest of the hatchetfish's anatomy supports this disappearing act. The body remains extremely thin from front to back, reducing the area that might cast a visible shadow. Large eyes point upward to watch for movement in the water above, while the mouth angles slightly toward the surface, ready to capture small animals drifting through the same region. Although the hatchetfish feeds on tiny prey, it spends much of its existence avoiding larger hunters that patrol these depths. Its luminous camouflage allows it to move quietly through water that might otherwise expose it. The fish does not rely on rapid swimming or sudden escapes. Instead, it depends on remaining unnoticed. Within the layered dimness of the ocean, the hatchet fish becomes a careful balance of shadow and light. Its glowing underside mirrors the faint radiance filtering from distant waters above, dissolving the outline of its body. To predators scanning the upward view, the fish fades into the background glow, a small presence that slips quietly through the depths without leaving a trace of its passage. Movement in the deep ocean often unfolds with a quiet patience that contrasts sharply with the restless activity of shallow seas. Instead of constant swimming or sudden chases, many predators drift slowly through the water, their bodies guided by subtle fin motions that disturb the surrounding currents as little as possible. Life in these depths rarely rewards rapid pursuit. The energy required for sustained speed would quickly exhaust animals that may wait long intervals between meals. For this reason, a large portion of deep-sea hunters rely on a different rhythm of survival. Their bodies are built to conserve rather than expend. Muscles remain efficient but not excessively powerful, and movements are measured with care. Even the shape of many predators reflects this economy. Long, narrow forms glide through the water with minimal resistance, allowing animals to maintain position or adjust direction without wasteful effort. The environment encourages this restraint. In places where food appears unpredictably, constant swimming would offer little advantage. A hunter might travel far through empty water without encountering prey, using precious energy for little return. Instead, many predators adopt a strategy based on patience, waiting for opportunities to drift within reach rather than seeking them through rapid motion. This quiet approach transforms the deep sea into a landscape of hidden observers. Animals position themselves carefully within the water column or near the contours of the seafloor. There, they remain almost motionless, allowing currents and wandering prey to bring movement toward them. From a distance, the predator may appear indistinguishable from the surrounding environment, another still presence in a vast and silent expanse. The moment of action arrives only when conditions align. A faint vibration passes through the water, or a small shape moves across the limited field of perception. Muscles that remained relaxed for long stretches of time suddenly engage. The predator closes the distance with a brief burst of motion, relying on precision rather than prolonged speed. Ambush tactics dominate many feeding encounters in this environment. By remaining still until the final instant, a hunter avoids alerting nearby animals through pressure waves or visible disturbance. The water around it remains calm, carrying little sign that a predator waits nearby. When the strike occurs, it unfolds with focused efficiency, often lasting only a fraction of a second. Some species anchor themselves near rocky outcrops or irregular terrain on the seafloor, using the landscape as natural concealment. Others hover within the water column, aligning their bodies vertically or at slight angles that reduce their outline against the surrounding darkness. In either case, the goal remains the same. The predator allows prey to approach closely before revealing its presence. This method of hunting shapes the entire pace of life in the deep ocean. Long intervals pass with minimal movement, broken only by brief episodes of decisive action. The balance between stillness and sudden motion becomes the defining rhythm of survival. Because of this pattern, speed has evolved differently in deep-sea species than in their shallow water relatives. Instead of maintaining high cruising velocities, many predators possess the ability to generate rapid acceleration over extremely short distances. Their muscles deliver concentrated bursts of force that propel the body forward just long enough to secure prey before returning to quiet drifting. Through these adaptations, the deep sea becomes a domain where silence itself functions as a hunting tool. The absence of unnecessary movement reduces disturbance in the water, preserving the element of surprise that ambush predators depend upon. Energy remains stored rather than spent, ready for the rare moment when prey enters reach. Within this patient world, predators drift like shadows suspended in water. They wait without urgency, guided by the understanding that movement alone does not guarantee success. In the vast stillness of the deep ocean, the most effective hunters often reveal themselves only at the final instant, when calm observation gives way to a swift and carefully timed strike. Some of the most revealing stories from the deep ocean are discovered only after an animal has been brought to the surface. When scientists examine preserved specimens, they sometimes open the stomach to understand what the creature last consumed. Inside these chambers of digestion, unexpected scenes occasionally appear, quiet records of encounters that unfolded far below. The contents are not always what researchers anticipate. A predator may contain prey almost equal to its own length, the body folded tightly inside the stomach. In other cases, the remains belong to species rarely seen together, suggesting that two animals from different parts of the deep environment crossed paths briefly before one became the other's meal. These findings reveal how unpredictable feeding encounters can be in such an immense and sparsely populated realm. Occasionally, the discoveries grow even stranger. Some predators are recovered with prey lodged partway down the throat, the swallowing process frozen at the moment it failed. The jaws remain locked around an animal that proved too large to move fully into the stomach. Both bodies remain intact, as though the event ended suddenly before digestion could begin. Such situations arise from the same pressure that shapes many deep-sea feeding strategies. When an opportunity appears, the predator often attempts to consume it immediately. There may be little time to judge whether the prey fits safely within the limits of the body. Instinct favors action over careful evaluation, especially in environments where encounters with food occur rarely. Most of the time, this strategy succeeds. Flexible jaws and expandable stomachs allow predators to handle prey larger than might seem possible at first glance. The tissues stretch gradually, accommodating the meal as it moves deeper into the digestive tract. Over hours or days, the stomach adjusts to the new volume, slowly breaking down the captured animal. Yet on rare occasions, the limits of anatomy become clear. If the prey exceeds the capacity of the predator's throat or stomach, the swallowing process may halt. The muscles responsible for guiding the meal downward cannot generate enough force to complete the movement, and the trapped body prevents the predator from closing its jaws or releasing the prey. In these unusual cases, the outcome can affect both animals involved in the encounter. The predator cannot feed successfully, yet the lodged prey blocks normal breathing or movement. Meanwhile, the captured animal remains immobilized, unable to escape from the teeth that hold it in place. The brief feeding attempt becomes a silent stalemate. Researchers studying deep-sea collections have documented several such examples. A well-known case involves a fish found with another large species protruding from its mouth, the prey nearly identical in size to the predator itself. The attempted meal became permanently fixed halfway through the act of swallowing, leaving both animals preserved together. These events remain uncommon, yet they provide insight into the risks associated with opportunistic feeding. The deep sea rewards creatures that seize available energy without hesitation, but the same urgency occasionally leads to encounters that exceed physical limits. Through careful examination of stomach contents and preserved specimens, scientists gain glimpses of these hidden interactions. Each discovery becomes a small window into the lives of animals rarely observed in their natural surroundings. The evidence does not show the full moment of the encounter, yet the arrangement of bodies hints at the struggle that took place. Within the immense quiet of the deep ocean, feeding attempts unfold quickly and often without witnesses. Most end with a successful capture that disappears into the digestive system of the predator. A few leave behind unusual records, revealing how the pursuit of scarce nourishment sometimes leads to encounters where the outcome remains suspended between hunter and prey. Within the deep ocean, recognition between species often becomes uncertain. Many animals move through water that offers little visual clarity, relying instead on fragments of sensory information carried through darkness. Shapes remain indistinct, outlines softened by distance, and movement often reveals itself only through faint disturbances in the surrounding water. In such conditions, the difference between familiar neighbor and potential meal can become difficult to determine. For this reason, cannibalism appears with surprising frequency among deep-sea predators. A fish encountering another individual of its own species may respond to the same signals that trigger any feeding response. The motion of a nearby body, the vibration of swimming muscles, or the chemical traces drifting through the water can all suggest the presence of prey. Without clear visual confirmation, instinct favors immediate action. In many cases, the encounter begins exactly as any other feeding opportunity would. Two animals approach the same region from different directions, each following subtle cues carried through the water. When their paths intersect, one may detect the movement first and initiate an attack before the identity of the other becomes clear. By the time recognition might occur, the strike is already underway. The anatomy of deep-sea predators often reinforces this pattern. Large jaws and inward-pointing teeth secure anything that slips within reach, regardless of whether the captured animal belongs to a different species or the same one. Once the prey is seized, the feeding process continues according to the same mechanical sequence that governs any successful hunt. Cannibalism does not necessarily represent aggression in the way it might appear from a human perspective. Instead, it reflects the practical demands of survival in an environment where nourishment remains unpredictable. Each encounter carries potential value, and the instinct to capture available energy often outweighs the advantage of distinguishing between individuals of the same species. Young animals sometimes face particular risk. Smaller members of a species drifting through the same region as larger adults may trigger the same feeding response that would occur toward unrelated prey. In the absence of strong visual signals or social behaviors, size differences alone may determine the outcome of such meetings. Evidence of this behavior frequently appears in the stomach contents of collected specimens. Researchers occasionally find individuals containing remains of their own species, the bones and scales, confirming that the predator consumed a close relative rather than a different animal. These discoveries reveal how commonly opportunistic feeding extends even to members of the same population. The structure of deep-sea ecosystems allows such behavior to persist without destabilizing the species involved. Populations remain widely dispersed across enormous areas of water, reducing the likelihood of repeated encounters between closely related individuals. Cannibalism therefore becomes one part of a broader feeding strategy rather than a dominant source of nutrition. In this environment, animals rarely develop the complex social recognition systems found in some shallow water species. There are no schools moving in coordinated patterns, no visual displays identifying individuals as members of the same group. Instead, Most creatures drift alone through the water column, guided by instinct and simple sensory cues. As a result, encounters between members of the same species often unfold in the same manner as any other meeting between predator and prey. The signals that trigger feeding remain unchanged, and the response occurs with similar speed and decisiveness. Within the deep ocean's vast darkness, survival depends on responding quickly to the limited opportunities that arise. The absence of clear recognition allows cannibalism to emerge naturally from this pattern. Each meeting between animals carries the potential to become a feeding event, even when the two participants share the same lineage, their paths crossing briefly within the immense and quiet expanse of the sea. Over long stretches of evolutionary time, the deep ocean has become a quiet stage for continual adaptation. Each generation of animals inherits subtle advantages from the last, small changes that improve survival in a world where encounters remain unpredictable. Gradually, these changes accumulate, shaping both hunters and the creatures that attempt to avoid them. What emerges is a slow contest of refinement, an ongoing adjustment between those that pursue and those that resist. For predators, one of the most valuable improvements involves perception. In darkness, where visibility remains limited, the ability to detect faint signals offers a clear advantage. Many hunters possess enlarged sensory organs capable of registering the slightest movement in the surrounding water. Fine structures along the body respond to shifts in pressure created by swimming animals, allowing predators to locate nearby life even when direct sight remains impossible. Vision also continues to evolve within these depths, though it takes on forms suited to dim environments. Some species develop large, sensitive eyes capable of capturing the smallest glimmer produced by another organism. Others specialize in recognizing brief flashes of bioluminescent light, turning momentary signals into guides that reveal the presence of prey. While predators refine their senses, potential prey undergo changes of their own. Animals that can avoid detection gain a greater chance of surviving long enough to reproduce. Over time, this pressure shapes bodies that minimize visibility and reduce the signals that predators rely upon. Many species develop transparent tissues or reflective surfaces that scatter incoming light, making their outlines difficult to distinguish. Armor represents another path of defense. Some deep-sea creatures possess rigid outer coverings that resist the bite of approaching predators. Thick scales, reinforced shells, or hardened plates protect the softer tissues beneath. These structures do not guarantee safety, yet they increase the effort required for a successful attack. Predators respond to these defenses through further adaptation. Teeth become stronger and more sharply curved, capable of penetrating protective layers that once provided reliable shelter. The arrangement of the jaws changes as well, allowing hunters to apply greater pressure during the act of biting. Over many generations, the interaction between predator and prey gradually reshapes both participants. This exchange rarely produces a final victory for either side. When a defensive feature spreads through a population, predators that overcome it gain a new advantage. Their descendants inherit the ability to handle prey that others cannot. In response, prey species continue to refine their defenses, creating new variations that reduce the success of hunters. The process unfolds slowly across thousands or millions of years, yet its results appear throughout the deep sea. A predator's teeth may seem unusually long or sharply angled, reflecting a lineage shaped by the need to seize well-protected prey. Nearby animals may display rigid outer layers or flexible spines designed to discourage capture. Even subtle traits contribute to this balance. The texture of skin, the placement of sensory organs, and the arrangement of body plates all reflect adjustments made over countless generations. Each small change represents the outcome of many encounters, most of which left no visible trace except the survival of those best suited to endure. Within the deep ocean, this gradual contest continues without pause. Predators refine their senses to locate hidden animals, while prey evolve structures that reduce the chance of detection or resist the moment of attack. Teeth meet armor, perception meets concealment, and both sides respond to the pressures imposed by the other. Across the vast darkness, this quiet exchange shapes the living forms that inhabit the depths. No single adaptation ends the process. Instead, the balance shifts slowly over time, guiding the evolution of creatures that remain locked in a patient and enduring relationship between pursuit and escape. Light in the deep ocean often carries meaning far beyond simple illumination. A brief flash may signal the presence of prey, the movement of a neighbor, or the sudden alarm of an animal attempting to escape. Because vision depends so strongly on bioluminescence in these depths, many species have learned to shape light into a form of communication. Over time, this reliance on glowing signals has created opportunities for deception. Certain animals produce patterns of light that function as lures, drawing curious creatures closer than they might otherwise approach. The glow may pulse gently or move in subtle arcs through the water, suggesting the motion of something small and edible. A drifting predator observing this display may interpret the signal as the presence of vulnerable prey. By the time the hunter moves within reach, the situation often proves quite different from what the light implied. Some deep-sea species extend this idea further by creating sudden flashes that imitate distress. In shallow waters, animals under attack often release bursts of light when disturbed. These flashes can attract other predators that rush toward the activity, hoping to claim a portion of the struggle. In the deep sea, certain organisms appear to mimic this reaction deliberately, producing rapid pulses that resemble the signals of a creature in danger. The result can confuse the predator that initiated the encounter. A hunter, approaching what appears to be an injured animal, may suddenly find the water around it illuminated by multiple sources of light. Other predators might converge toward the glow, shifting the balance of the interaction. The original hunter risks becoming visible to larger animals that interpret the flashes as an opportunity of their own. Bioluminescent deception also appears in the form of decoys. Some organisms release small luminous particles into the water when threatened. These glowing fragments drift away like tiny stars, forming a scattered cloud that distracts the attention of nearby predators. While the hunter focuses on the moving lights, the animal that produced them slips quietly away into the surrounding darkness. Other species carry light-producing organs positioned in ways that redirect attention. A small glow may appear at the tip of a moving appendage or along the edge of the body, encouraging a predator to strike at a less vital area. When the attack lands on the decoy rather than the main body, the prey gains a moment to escape. These strategies rely on the deep ocean's dependence on visual signals. In water where other sensory information remains faint or delayed, a sudden light can command immediate attention. Predators learn to associate glowing movement with the possibility of food, and prey species use that expectation to reshape the outcome of encounters. The chemistry behind these displays remains similar across many organisms. Inside specialized cells, molecules interact with oxygen in reactions that release energy as visible light. By controlling when and where these reactions occur, animals produce patterns that vary in brightness, duration, and color. Each variation becomes part of a signal that other creatures interpret according to their own instincts. Over generations, this exchange between signal and interpretation has encouraged increasingly elaborate uses of bioluminescence. Hunters learn to exploit light as a lure, while potential prey develop ways to redirect or disrupt the expectations of those hunters. The water becomes a stage where flashes and glows carry meaning that shifts from moment to moment. Within the quiet depths, these luminous interactions unfold silently. A small flicker may drift through the water, unnoticed by some animals, yet irresistible to others. Sometimes the light leads directly to a successful capture. At other times, it becomes a carefully crafted illusion, guiding attention away from the creature that produced it. In this environment, light no longer serves merely to reveal the presence of life. It becomes a tool of persuasion, capable of drawing predators toward false targets or inviting them into encounters shaped by deception. Through countless variations of glow and motion, animals transform bioluminescence into a subtle language of trickery that moves quietly through the deep ocean. Drifting quietly through the deep ocean lives an animal whose appearance suggests a creature from distant imagination. The vampire squid moves with slow, deliberate motions, its soft body suspended between long, delicate arms connected by a thin web of tissue. Despite the name, this species does not hunt other animals in the dramatic manner its title implies. Instead, it survives largely by gathering drifting organic material from the surrounding water. Its most remarkable features appear not during feeding, but when danger approaches. Unlike many squid that rely on speed to escape predators, the vampire squid inhabits depths where energy must be conserved carefully. Its muscles are not designed for sustained bursts of rapid swimming. Instead, the animal carries a collection of defensive adaptations that allow it to respond to threats without prolonged effort. One of the most unusual responses involves a posture that transforms the entire shape of the animal. When disturbed, the vampire squid can draw its arms backward over the body, turning the webbed membrane inside out. The motion encloses the softer surfaces within a protective layer of darker tissue while exposing rows of small spines that line the inner side of the arms. In this configuration, the animal resembles a floating sphere edged with slender projections, a shape that discourages predators from attempting an easy grasp. While holding this posture, the vampire squid may release a cloud of luminous particles into the water. These glowing fragments function in a way similar to the ink clouds produced by other cephalopods, yet they carry an additional element. Each particle emits a soft bioluminescent glow as it spreads through the surrounding currents. The result is a drifting cloud of light that lingers briefly in the water. Predators approaching the squid suddenly encounter a confusing scene. Instead of a single moving target, the water becomes filled with slowly dispersing points of light. These glowing particles scatter attention across a wide area, interrupting the predator's focus on the animal that released them. While the luminous cloud spreads outward, the vampire squid moves quietly away, using gentle pulses of its fins. The motion remains controlled and efficient, allowing the animal to retreat without drawing additional attention. In the dim water, the glowing particles continue to drift behind it, holding the predator's gaze for precious moments. Another feature assists this defensive strategy. The vampire squid possesses highly sensitive photoreceptors, capable of detecting subtle changes in light. If a predator approaches carrying its own bioluminescent signals, the squid may recognize the disturbance early and prepare its response before the hunter comes close. The body of the vampire squid also reflects a design suited for survival in low-oxygen environments common in certain deep ocean layers. Its blood contains pigments that bind oxygen efficiently, allowing the animal to remain active in water where many predators experience difficulty maintaining prolonged effort. This physiological advantage can provide an additional margin of safety during slow retreats from danger. Unlike animals that rely on aggression or speed, the vampire squid survives by reshaping the moment of encounter. Defensive postures alter its silhouette, luminous particles redirect attention, and controlled movement guides the animal away from immediate risk. Each response unfolds with measured precision rather than sudden violence. Through these adaptations, the vampire squid demonstrates how survival in the deep sea does not always depend on overpowering an opponent. In an environment where energy remains precious and visibility limited, subtle strategies often prove more reliable. By combining protective posture, glowing distractions, and quiet retreat, the animal transforms potential attacks into brief interruptions within its slow passage through the depths. In the silent layers of the deep ocean, the vampire squid continues its drifting journey, prepared to dissolve into clouds of light whenever a predator draws near. Along the deep seafloor, where the sediment stretches outward in quiet plains, certain animals spend their lives in patient expectation. Among them moves the giant isopod, a crustacean whose body resembles that of a familiar woodlouse, though its size is far greater than any relative found on land. Its segmented shell forms overlapping plates that curve gently along the back, while multiple jointed legs carry it slowly across the soft ocean floor. The giant isopod belongs to a group of scavengers that rely on food arriving from distant sources. Rather than hunting living prey, these animals search the seabed for the remains of creatures that have already died. A fish drifting downward from the water above, a squid weakened after injury, or fragments of larger animals may eventually settle onto the sediment. Each arrival becomes a rare opportunity for nourishment. Between these events, the isopod continues its slow journey through the darkness. Its movements remain measured and deliberate, conserving energy as it explores the surrounding terrain. The animal's compound eyes, adapted to faint light, assist in detecting subtle changes in the environment, yet vision alone does not guide its search. Chemical cues drifting through the water also reveal the presence of decaying organic matter somewhere nearby. These signals travel gradually across the seafloor, carried by gentle currents. When the scent of potential food reaches a giant isopod, the animal adjusts its direction and begins moving toward the source. Other scavengers may detect the same trace, and from several directions, different species start converging on the same distant location. For long periods, the isopod may encounter nothing at all. Months can pass without a substantial meal. During these quiet intervals, the animal survives on remarkably low metabolic activity, conserving stored energy within its tissues. This ability allows it to endure extended scarcity while continuing its slow search across the seabed. When food finally arrives, the stillness of the seafloor changes rapidly. A fallen animal resting on the sediment releases chemical signals that spread outward like an invisible invitation. Giant isopods begin appearing from the surrounding darkness, their segmented bodies approaching from many directions. Alongside them come other scavengers, including fish, crabs, and smaller crustaceans. As more animals gather, the scene becomes a feeding aggregation. The giant isopods climb onto the remains, their legs gripping the surface while their mouthparts begin to tear and consume soft tissue. Their armored bodies press close together as multiple individuals feed at once. each attempting to secure as much nourishment as possible before the opportunity disappears. During these feeding periods, the behavior of the isopods changes noticeably. Normally slow and reserved, they move with greater urgency across the carcass, adjusting position to reach new areas of flesh. Competition among scavengers encourages rapid consumption. Every participant attempts to claim its share before the resource is exhausted. The giant isopod possesses an abdomen capable of expanding dramatically during such meals. As it feeds, the body gradually swells with stored nutrients that will sustain the animal through the next extended period of scarcity. Once the carcass has been reduced to fragments, the isopods detach and return to their solitary wandering across the sea floor. Over time, the remains disappear entirely, consumed by the gathering of scavengers and the microscopic organisms that complete the final stages of decomposition. The seabed returns to quiet stillness once more. Giant isopods resume their slow movement through the sediment, their bodies carrying the energy obtained from the recent feast. Within this patient cycle, the giant isopod reflects a different form of survival in the deep sea. Instead of pursuing living prey, it relies on endurance and careful conservation of energy. Long intervals of waiting alternate with brief moments of intense feeding activity. Through this rhythm of scarcity and sudden abundance, the isopod continues its quiet existence across the silent floor of the deep ocean. Far above the seafloor, yet still within the immense darkness of the deep ocean, one of the planet's largest predators descends on quiet columns of water. The sperm whale moves downward with powerful strokes of its tail, its massive body built for journeys that carry it far beneath the surface world. With each dive, the whale enters regions where sunlight no longer reaches, navigating depths that remain hidden from human sight. These descents are not brief explorations. A sperm whale may remain submerged for nearly an hour while searching for food in the deep ocean. Its body contains specialized adaptations that allow it to tolerate the immense pressure and limited oxygen of these depths. Muscles store large amounts of oxygen-binding proteins, while the lungs collapse safely during the descent, reducing the effects of pressure on internal tissues. Within this vast underwater territory lives another remarkable creature, the giant squid. Unlike the whale, which must eventually return to the surface to breathe, the squid spends its entire life within the deep water column. Its body remains long and flexible, with powerful tentacles extending forward to capture prey. Large eyes, among the biggest found in the animal kingdom, allow it to detect faint movement or distant silhouettes in the surrounding darkness. Encounters between these two animals rarely occur in view of observers, yet evidence of their interactions appears in several forms. When sperm whales return to the surface after deep dives, researchers often notice unusual markings on their skin. Circular scars sometimes cover the head and flanks of the whale, arranged in patterns that match the shape of large suction cups. These marks reveal traces of encounters with squid during the whale's hunts. As the whale closes in on its prey, the squid may respond by extending its tentacles, attempting to grip the approaching predator with rows of powerful suction cups lined with small teeth. The suction cups attach briefly to the whale's skin, leaving behind round impressions that remain visible long after the struggle ends. For the whale, the hunt depends heavily on sound rather than vision. Sperm whales produce intense clicks that travel through the water as pulses of echolocation. When these sound waves strike an object, the returning echoes reveal the location, size, and movement of animals nearby. Through this acoustic sensing, the whale can detect squid moving in the dark water around it. Once the whale locates its target, the encounter likely unfolds rapidly. The powerful predator approaches with strong strokes of its tail, while the squid attempts to defend itself using its tentacles and sharp hooks along the gripping surfaces of its arms. The interaction may last only a brief moment before the whale captures and swallows the squid. Evidence of these events also appears in the stomach contents of sperm whales, examined by researchers. Remains of squid, including beaks that resist digestion, accumulate within the digestive system. These structures confirm that squid form a significant part of the whale's diet during its deep ocean dives. Despite the immense size of the sperm whale, the squid does not remain defenseless during these encounters. The scars visible on whale skin show that the struggle can leave lasting marks on the predator. Each circular imprint reflects a moment when the squid resisted capture, pressing its suction cups firmly against the whale's body before the encounter ended. Through these traces, scientists piece together one of the deep ocean's most dramatic interactions. The whale descends from the surface with the advantage of mass and echolocation, while the squid waits within the darkness with long arms prepared for defense. Their meeting remains hidden within depths rarely witnessed directly. Within this quiet region of the ocean, the contest between sperm whale and giant squid continues without spectacle. The evidence appears only afterward, etched into the skin of a returning whale or preserved within the remains carried to the surface. From these clues emerges the outline of a struggle between two extraordinary animals sharing the same remote world beneath the waves. In certain depths of the Southern Ocean, a large cephalopod moves slowly through the cold water column, its body built with features rarely seen in other squid. Known as the colossal squid, this animal carries a set of defensive and hunting structures that remain concealed until the moment they are needed. Much of its life unfolds far beyond the reach of ordinary observation, yet the anatomy of recovered specimens reveals a creature equipped with unusual tools for survival. The most striking of these tools appears along the tentacles. While many squid rely primarily on suction cups to grip prey, the colossal squid adds an additional structure that changes the nature of its grasp. Embedded among the suckers are sharp hooks capable of rotating slightly as they make contact. These hooks curve inward, forming small barbed points that hold firmly once they attach to flesh. When the tentacles extend toward prey, the hooks engage almost instantly. Their rotation allows them to anchor securely within soft tissue, preventing the captured animal from pulling free. This gripping system proves effective not only for capturing food, but also for resisting the force of predators that attempt to seize the squid during an encounter. Supporting this physical defense are the colossal squid's remarkable eyes. Each eye grows to an extraordinary diameter, larger than those of any other known animal. These enormous organs gather faint light across a wide surface, allowing the squid to perceive subtle disturbances in the surrounding water. Even the dim glow produced by distant organisms or the shadow of a large body moving through the depths may become visible through this expansive field of vision. Such sensitivity offers an advantage in detecting approaching threats. When a large predator descends through the water column, its presence may disturb small bioluminescent organisms drifting nearby. The movement can trigger faint flashes of light that ripple through the darkness. With its large eyes, the colossal squid may notice these disturbances early enough to prepare for an encounter. Among the predators capable of challenging the squid stands the sperm whale, an animal whose deep diving hunts bring it into the same cold waters. When such a predator approaches, the squid relies on both its size and its defensive structures. The muscular arms extend outward, while the hooked tentacles remain ready to grasp anything that comes within reach. If contact occurs, the rotating hooks provide the squid with a powerful grip. These structures can press firmly into the skin of a predator, anchoring the tentacles while the squid attempts to maintain distance. The hooks leave distinctive circular marks that remain visible on whale skin long after the encounter has ended. The squid's body also contributes to its defense. Its mantle contains strong muscles capable of producing bursts of propulsion through jet movement. By forcing water rapidly through its siphon, the squid can accelerate away from danger for short distances, creating space between itself and an approaching predator. Despite these formidable traits, the colossal squid does not spend its life in constant conflict. Much of its existence likely passes in quiet movement through cold, deep waters where encounters remain infrequent. During these long intervals, the animal drifts slowly, its large eyes scanning the surrounding darkness while its tentacles remain folded close to the body. Yet, when another large animal enters this hidden world, the squid carries the equipment needed to respond. Rotating hooks grip firmly, powerful arms resist capture, and immense eyes monitor the faint signals that reveal approaching movement. Through this combination of sensory awareness and physical defense, the colossal squid maintains its place within the deep ocean ecosystem. Its tools remain concealed during quiet moments, yet they form a hidden arsenal shaped by countless generations adapting to life among the largest hunters of the sea. In certain regions of the deep ocean, animals appear in forms that seem unexpectedly large compared with their relatives in shallower waters. A crustacean that resembles a familiar shoreline species may grow to the size of a dinner plate. Worms extend far longer than their coastal counterparts, and soft-bodied creatures drift through the water with proportions that seem almost exaggerated. This pattern, often called deep-sea gigantism, reflects the unusual environmental conditions that shape life far below the surface. One factor influencing this growth lies in the temperature of the surrounding water. At great depths, the ocean remains close to freezing, with only slight variations across vast areas. Cold conditions slow many biological processes, including the rate at which cells divide and tissues develop. Animals living within these temperatures often grow gradually over extended periods of time, adding small increments of mass year after year. Because life in the deep sea tends to progress slowly, some species reach maturity much later than similar animals living in warmer environments. The extended lifespan allows their bodies to continue increasing in size long after shallow water relatives would have stopped growing. Over generations, this pattern produces populations in which large individuals become common. Metabolism also plays an important role in shaping these forms. In cold water, the chemical reactions that sustain life occur at a slower pace. Energy is used carefully and released gradually. Animals that maintain low metabolic demands can survive with fewer meals, storing energy within their tissues and using it sparingly over long intervals. Larger bodies provide certain advantages under these conditions. A greater volume allows animals to store more energy reserves, helping them endure periods when food remains scarce. The surface area of the body grows more slowly than the internal volume, reducing the rate at which energy escapes to the surrounding water. This balance supports survival in environments where new resources arrive unpredictably. Pressure may also influence the shape and size of deep-sea organisms. At extreme depths, the weight of the water above creates immense compression. Many animals possess flexible tissues that adapt easily to these forces. Without rigid skeletons restricting growth, some species develop broad or elongated forms that distribute pressure evenly across the body. Examples of this phenomenon appear throughout the deep ocean ecosystem. The giant isopod, a distant relative of small terrestrial woodlice, grows to impressive dimensions as it moves across the seabed. Amphipods, which resemble tiny shrimp in shallow waters, sometimes reach sizes several times larger in deep environments. Even delicate animals such as sea spiders develop unusually long legs that extend widely across the seafloor. Certain cephalopods also display this tendency toward large size. Some squid inhabiting deep waters possess bodies and tentacles that stretch to remarkable lengths. These forms move slowly through the water column, their large dimensions allowing them to store energy while navigating a landscape where encounters remain unpredictable. Despite their scale, these animals often maintain the same quiet pace seen across much of the deep ocean. Large size does not necessarily bring rapid movement or constant activity. Instead, it becomes another expression of the patient rhythm that defines life in these depths. The growth of such organisms unfolds gradually across years, shaped by cold temperatures, slow metabolism, and the demands of an environment where energy arrives in irregular patterns. Through these influences, familiar body plans transform into larger versions of themselves, adapted to endure long intervals between opportunities. Within the silent waters far below the surface, gigantism becomes one more reflection of the ocean's unusual balance. Creatures expand in scale, while maintaining the same measured existence shared by many deep-sea inhabitants, their large forms drifting through a realm where time and growth proceed at a calm and deliberate pace. As depth increases beneath the ocean's surface, the weight of the water above grows steadily heavier. Every descending meter adds another layer, pressing downward until the pressure reaches levels difficult to imagine at the surface. In the deepest regions of the ocean, the force surrounding an animal can exceed 1,000 times the pressure experienced on land. Any air-filled structure would collapse immediately under such conditions, and many materials familiar in shallow environments would fail completely. Yet deep-sea animals move through this immense pressure without visible strain. Their bodies do not resist the weight in the same way surface organisms might attempt to do. Instead, they adapt by matching the pressure of their surroundings, allowing the forces outside and inside their tissues to remain balanced. Without large pockets of gas or rigid cavities, their bodies avoid the crushing effects that would otherwise occur. Most deep-sea creatures lack swim bladders, the gas-filled organs that help many fish control buoyancy near the surface. Gas compresses easily under pressure, and any such structure would shrink dramatically during descent. By replacing gas-filled spaces with fluid-filled tissues, deep-sea animals eliminate this vulnerability. Liquids resist compression far more effectively, maintaining stable volume even as the surrounding pressure rises. Cellular chemistry also changes in these environments. The molecules that form proteins and enzymes must continue functioning despite the intense pressure pressing on every cell. Many deep-sea species produce specialized compounds known as piezolites, small molecules that stabilize proteins and preserve their shape under compression. Without these chemical adjustments, essential biological reactions would slow or stop entirely. Bones and shells also respond to the demands of depth. Some species reduce the density of their skeletons, replacing rigid structures with softer, more flexible materials. Instead of resisting the surrounding pressure, these bodies yield slightly, distributing the force evenly across their tissues. The result is an anatomy that appears delicate yet functions reliably in extreme conditions. At first glance, many deep-sea animals seem fragile compared with their shallow water relatives. Their bodies often appear gelatinous, with thin muscles and translucent skin. These features reflect a design shaped by pressure and limited energy rather than brute strength. Thick, heavy tissues would require additional energy to maintain and move, a costly investment in an environment where food remains scarce. Despite this softness, Such animals remain capable predators. Their apparent fragility does not prevent them from capturing prey or defending themselves. Flexible bodies allow them to move quietly through the water with minimal disturbance, an advantage when approaching unsuspecting animals nearby. Many predators in the deep ocean rely on rapid mouth expansion or sudden tentacle extension rather than powerful bites delivered by rigid jaws. Soft tissues can expand quickly under the surrounding pressure, creating swift suction or grasping motions that secure prey before it has time to react. The absence of heavy skeletal structures often allows these movements to occur with remarkable speed. Even creatures that appear almost transparent may possess specialized organs capable of delivering precise strikes. Delicate arms lined with hooks, narrow teeth angled inward, or tentacles equipped with gripping surfaces provide efficient tools for capturing prey. These structures operate effectively because the surrounding water pressure supports the body, reducing the need for internal rigidity. Through these adaptations, the deep sea demonstrates how survival does not always require physical hardness. Instead, the environment favors flexibility, chemical stability, and anatomical designs that cooperate with the surrounding pressure rather than resisting it. Within the immense weight of the ocean depths, animals continue their quiet movements, their bodies shaped by forces far greater than those found near the surface. Soft forms glide through the water while maintaining the ability to capture prey and endure the conditions around them. In this world of immense pressure, resilience emerges not from rigidity, but from careful balance between body and environment. Far below the quiet plains of the deep seafloor, certain regions break the usual pattern of stillness. Along long fractures in the ocean crust, seawater seeps downward into the Earth's interior, where it encounters rock heated by molten material beneath the surface. The water returns upward through narrow openings, emerging from the seabed as dark, mineral-rich plumes. These places are known as hydrothermal vents, and they transform otherwise empty stretches of ocean floor into concentrated centers of life. From a distance, the vent fields resemble underwater chimneys rising from the sediment. Mineral particles carried in the superheated water settle rapidly as the fluid meets the surrounding cold ocean, forming towering structures of black and gray deposits. The water pouring from these vents can reach temperatures far hotter than the freezing environment around them, creating sharp contrasts within a small area. Despite the extreme conditions, living organisms gather densely around these openings. Unlike much of the deep sea, where energy arrives slowly from distant sources, hydrothermal vents provide a direct supply of chemical nutrients emerging from the earth itself. Microorganisms living near the vents use these compounds as an energy source through a process known as chemosynthesis. Instead of relying on sunlight, they convert chemicals such as hydrogen sulfide into organic material. These microorganisms form the foundation of an entire ecosystem. Their presence supports communities of animals that would rarely appear together in the surrounding depths. Tube worms extend long white bodies from protective sheaths anchored in the sea floor. Clusters of mussels attach themselves to the vent chimneys, while shrimp and crabs move among the crevices searching for food. Compared with the vast empty spaces beyond the vent field, these areas appear almost crowded. Animals gather in dense assemblages around the sources of chemical energy, their bodies forming layers of movement along the rocky surfaces. The surrounding water may remain dark and silent, yet within the boundaries of the vent community, life continues with steady activity. This concentration of organisms naturally brings competition. Many animals feed directly on the microbial growth coating the vent structures, scraping or filtering the bacteria that thrive in the chemical-rich environment. Others prey upon the smaller creatures that gather there, turning the crowded conditions into opportunities for hunting. Because the habitable space remains limited to the area surrounding the vents, animals must share the same narrow territory. Tube worms anchor themselves in dense clusters, while mussels grow closely together across the mineral surfaces. Mobile species such as crabs weave between these colonies, searching for food while avoiding larger predators that patrol the same ground. The conditions around hydrothermal vents can also change unexpectedly. As mineral deposits accumulate, or as the flow of heated water shifts beneath the seabed, some vents weaken while new ones emerge nearby. Entire communities may gradually migrate from fading vents toward fresh openings where chemical energy continues to rise from the Earth's interior. Within these shifting environments, animals compete not only for food but also for space close to the active vent fluids. The warm water and chemical nutrients provide advantages that cannot be found in the colder surroundings beyond the vent field. Remaining near these openings allows organisms to maintain access to the energy that sustains the ecosystem. Through this combination of concentrated resources and limited territory, hydrothermal vents create a rare form of intensity within the deep sea. Creatures that might otherwise drift alone across vast distances gather together in dense clusters, each relying on the same narrow supply of chemical nourishment. Against the quiet background of the surrounding ocean floor, these vent communities stand as small islands of activity. Mineral chimneys release their heated plumes. Microorganisms transform chemical compounds into living tissue, and animals crowd around the source of energy rising from the earth below. Within these confined spaces, life organizes itself around the steady flow of heat and minerals emerging from the hidden processes beneath the ocean crust. At first glance, some predators of the deep ocean appear almost invisible. Their bodies contain so little pigment that they blend with the surrounding water, leaving only faint outlines that shift gently with the currents. These animals belong to a wide group of gelatinous hunters, often described as deep-sea jellies. Their soft tissues and transparent forms allow them to move through the water in a manner that seems nearly effortless. Unlike many predators that rely on rapid motion, these organisms drift quietly through the water column. Their bodies pulse slowly, contracting and relaxing in rhythmic movements that push them forward with delicate propulsion. Each pulse sends a small ring of water outward, carrying the animal along without creating strong disturbances that might alert nearby prey. The structure of these predators often centers around long, slender tentacles that extend outward into the surrounding water. Some species trail only a few delicate filaments, while others release dozens of thin threads that stretch many times the length of the body itself. These tentacles form a wide capture zone that drifts silently through the dark ocean. Along the surface of each filament lie specialized cells known as nematocysts. These microscopic structures contain tightly coiled harpoons capable of firing outward when touched. When a small animal brushes against the tentacle, the harpoon discharges instantly, delivering a tiny dose of toxin and anchoring the prey to the filament. Because the tentacles remain almost invisible in the water, many animals encounter them without warning. A small crustacean drifting through the current may pass directly into the web of filaments, triggering multiple nematocysts at once. The prey becomes entangled among the sticky threads as the toxin begins to take effect. Once captured, the tentacle gradually contracts, drawing the immobilized prey closer to the main body of the predator. The movement remains slow and controlled, conserving energy while guiding the captured animal toward the mouth. Within moments, the prey disappears into the soft opening where digestion begins. Some deep-sea jellies rely on particularly elaborate tentacle structures. Certain species arrange their filaments into branching patterns that resemble delicate underwater nets. These nets spread outward across large volumes of water, increasing the likelihood that drifting animals will encounter them. Others produce mucus along their tentacles, creating surfaces that adhere lightly to passing prey. The sticky coating traps small organisms long enough for the predator to reel them inward. Even creatures that escape the initial sting may find themselves caught within this gelatinous web. The transparency of these animals provides an additional advantage. Light passing through their bodies scatters only slightly, leaving little visual contrast against the surrounding water. Predators and prey alike may overlook them entirely until contact with the tentacles reveals their presence. Despite their gentle appearance, these organisms remain effective hunters within the deep ocean ecosystem. Their bodies require relatively little energy to maintain, allowing them to survive in environments where food may appear unpredictably. By expanding their tentacles across wide areas, they allow the currents to deliver prey directly into their grasp. Many species also possess bioluminescent features that produce faint glows along their bodies or tentacles. These lights may attract curious animals or confuse larger predators approaching from a distance. The glowing patterns drift slowly through the darkness, adding another layer of subtlety to their hunting strategy. Within the quiet depths, these gelatinous predators create traps that rely on patience rather than pursuit. Their bodies float lightly in the water, tentacles extended like invisible threads waiting for contact. Each passing current carries the possibility that an unwary animal will brush against the delicate filaments. Through transparency, sticky tentacles, and silent drifting, deep-sea jellies transform the surrounding water into a field of hidden snares. In a world where movement often remains slow and encounters rare, these nearly invisible hunters allow the ocean itself to deliver their prey. Some predators of the deep ocean rely less on careful selection and more on absolute opportunity. In an environment where food appears unpredictably, hesitation can mean long periods without nourishment. For certain species, survival depends on the ability to consume whatever drifts within reach, regardless of size or identity. Among the most striking examples of this strategy is a small but remarkable fish known as the black swallower. The body of the black swallower appears slender and modest in length, often no longer than a human hand. Its dark skin absorbs nearly all surrounding light, leaving only the outline of its shape visible against the water. Yet within this compact body lies an anatomical design that allows the fish to attempt meals far larger than its own size. The jaws form the first part of this unusual system. Unlike rigid skull structures that restrict the opening of the mouth, the bones of the black swallower connect through flexible joints and elastic ligaments. When the mouth opens, the lower jaw drops downward, while the upper structures rotate slightly outward, creating a surprisingly wide gap. This flexibility allows the fish to begin swallowing prey that would appear impossible for its size. Inside the mouth, narrow teeth angle inward like slender hooks. These teeth do not slice or tear in the manner of cutting blades. Instead, they function as a barrier that prevents captured prey from escaping once it enters the throat. Any movement by the struggling animal pushes it deeper between the teeth, guiding it toward the digestive tract. The stomach provides the second element of the swallower's remarkable adaptation. Unlike the fixed stomachs found in many fish, This organ expands dramatically when filled. The walls consist of elastic tissue capable of stretching to several times their resting size. When a large prey item passes into the stomach, the body of the predator adjusts around it, accommodating the unexpected volume. As digestion begins, the fish may appear transformed. Observers who recover specimens sometimes find individuals with swollen abdomens containing prey nearly equal to their own length. The body stretches around the captured animal, creating a temporary shape that reflects the scale of the meal hidden inside. This strategy allows the black swallower to exploit rare opportunities when they appear. A fish passing through the water column may encounter prey that exceeds its own mass, yet the predator still attempts to swallow it. If successful, the resulting meal can provide enough energy to sustain the animal through extended periods without food. The digestive process unfolds gradually after such encounters. Enzymes break down the tissues of the prey over time, releasing nutrients that the predator stores within its body. As digestion progresses, the stomach slowly contracts, returning the fish to its original slender form. Despite the remarkable capacity of this system, it carries certain risks. If the prey proves too large or begins to decompose before digestion is complete, gases produced within the stomach may cause the body to expand further. In some recorded cases, this expansion forces the predator upward through the water column, revealing specimens floating near the surface with oversized meals still inside. Yet the persistence of this feeding strategy across generations suggests that its advantages outweigh the occasional dangers. In the deep ocean, where encounters remain rare and unpredictable, the ability to seize a single, enormous meal can determine whether an animal survives the long intervals that follow. Through flexible jaws, inward-pointing teeth, and an expandable stomach, the black swallower embodies a philosophy of survival shaped by scarcity. The fish does not wait for prey that fits neatly within its limits. Instead, it attempts to consume whatever opportunity appears, trusting its extraordinary anatomy to handle the consequences. Most encounters in the deep ocean pass without witnesses. The immense volume of water spreads life across distances so large that even powerful research equipment observes only a small portion of the environment at any moment. Cameras lowered into the depths often remain fixed in a single location, recording long stretches of drifting particles, quiet currents, and the occasional passing animal. The dramatic moments of hunting and struggle rarely unfold directly in front of these lenses. Part of this difficulty comes from the scale of the deep sea itself. The regions where many predators live extend for thousands of meters in every direction. Even when a submersible or remote camera explores these depths, the field of view remains narrow compared with the surrounding expanse. Two animals may encounter one another only briefly before moving beyond the reach of observation. Another factor lies in the timing of these events. Many predatory strikes occur within fractions of a second. A fish may drift motionless for long intervals, conserving energy while waiting for movement nearby. When prey enters the small area within reach, the predator reacts instantly. The attack unfolds so quickly that a stationary camera may capture only the aftermath, revealing the predator already holding its meal. Because these encounters remain difficult to record directly, scientists often rely on indirect evidence to understand what occurs in the darkness below. One of the most valuable sources of information comes from injuries observed on living animals. Scars, missing limbs, and unusual markings on the skin can reveal previous interactions with predators. Circular impressions left by suction cups, narrow punctures from teeth, or scratches along protective shells all hint at earlier struggles that took place unseen. Each mark represents a moment when two animals crossed paths in the depths, leaving behind a record etched into the body of the survivor. Stomach contents provide another window into these hidden events. When researchers examine specimens collected from deep water, the remains of prey found inside predators can reveal surprising relationships between species. A fish recovered from great depth may contain another animal rarely observed in the same location, suggesting that their paths crossed during a brief feeding encounter. These discoveries sometimes challenge earlier assumptions about how certain species behave. Animals thought to occupy separate regions of the ocean may appear together within the digestive tract of a predator, indicating that their movements occasionally overlap. Through such evidence, scientists gradually piece together the feeding networks that shape life in the deep sea. Submersibles and remotely operated vehicles have begun to expand these observations, allowing researchers to spend longer periods exploring deep environments. Even with these tools, however, the probability of witnessing an active hunt remains small. The ocean floor and water column contain countless animals, yet their meetings occur across a landscape too vast for consistent observation. For this reason, much of the deep sea's most intense activity remains hidden from view. Predators drift patiently through the water, prey move cautiously through the same spaces, and their encounters unfold in moments that rarely coincide with the presence of cameras. What researchers do capture often consists of subtle clues rather than complete scenes. A predator holding newly captured prey, an animal bearing fresh injuries, or a specimen containing an unexpected meal can reveal that an encounter occurred shortly before observation. Through these fragments of evidence, a picture slowly emerges of the interactions shaping life in the deep ocean. Although direct recordings remain rare, the traces left behind allow scientists to reconstruct many of the events that unfold in this distant environment. Within the immense darkness, countless struggles occur every day, yet only a small number enter the human record. Most pass quietly through the depths, leaving behind nothing more than the marks carried by the animals that survived them. Across the vast depths of the ocean, knowledge advances slowly, carried downward by machines built to withstand pressure and darkness. For much of human history, the deep sea remained unreachable, its inhabitants known only through fragments brought accidentally to the surface. In recent decades, however, new exploration technologies have begun to extend observation into places that once remained completely hidden. Research vessels now deploy remotely operated vehicles capable of descending thousands of meters beneath the waves. These machines travel along the seafloor or drift through the water column, guided by cables that transmit video and data back to scientists waiting on the ship above. Powerful lights illuminate the surrounding water, while high-resolution cameras record the movements of animals rarely seen before. Autonomous vehicles provide another method of exploration. Unlike remotely operated systems, these machines move independently once released into the ocean. Equipped with sensors and navigation systems, they travel pre-programmed paths across deep environments, collecting images and environmental measurements before returning to the surface. Submersibles designed to carry human observers have also opened new perspectives. Within reinforced pressure spheres, scientists descend directly into the deep ocean, watching the surrounding ecosystem through small windows. These journeys allow researchers to observe the behavior of animals in real time, capturing details that might otherwise pass unnoticed. Through these technologies, discoveries continue to emerge each year. New species appear regularly in scientific records, expanding the known diversity of deep-sea life. Some animals display forms and adaptations unlike anything previously documented. Transparent organisms with delicate structures drift through the water column, while unfamiliar fish glide slowly above the seafloor with features suited precisely to their environment. In certain cases, species that once seemed rare prove to be widespread once scientists begin looking more closely. The deep sea contains enormous regions that remain unexplored, and each expedition reveals animals that had never been observed by humans before. Even in areas that have been visited repeatedly, unexpected organisms sometimes appear within camera frames. These discoveries extend beyond the identification of new species. Researchers also begin to uncover complex relationships among animals that share the same environment. Predator and prey interactions, migration patterns, and feeding behaviors gradually become clearer as more observations accumulate. Yet many connections remain uncertain. Because encounters occur across such immense distances, the full structure of deep-sea food webs still contains large gaps. Scientists may know that a particular predator consumes certain animals, yet the complete range of its prey remains unknown. Similarly, some species appear frequently in camera recordings, but their role within the ecosystem remains difficult to interpret. Technological progress continues to narrow these uncertainties. Improved imaging systems allow researchers to record longer periods of deep-sea activity without disturbing the animals being observed. Environmental DNA sampling provides another tool, allowing scientists to detect the genetic traces left behind by organisms passing through an area even when the animals themselves remain unseen. Through these methods, patterns slowly emerge from the darkness. Each observation adds another piece to the growing understanding of how life functions in one of Earth's largest habitats. The deep sea begins to reveal connections between species that once appeared isolated from one another. Even with these advances, however, much of the ocean remains unexplored. Vast regions of the seafloor have never been visited by research vehicles, and many species likely move through environments that cameras have not yet reached. As exploration continues, the deep ocean offers a steady reminder that scientific discovery often unfolds gradually. Each expedition expands the boundary of knowledge, revealing new forms of life and unexpected relationships among the animals that inhabit this remote environment. Beneath the waves, an enormous portion of Earth's living world still waits to be observed and understood. Movement in the deep ocean often travels farther through water than through sight. In places where darkness limits visual information, animals depend on the subtle language carried by pressure waves and shifting currents. Each motion made by a swimming body pushes water outward in faint pulses, spreading vibrations that ripple across the surrounding environment. For creatures adapted to these signals, the ocean becomes a field of invisible motion. Many deep-sea fish possess a sensory system designed specifically to interpret these disturbances. Running along the length of their bodies lies a structure known as the lateral line. Beneath the skin, this line contains small fluid-filled canals connected to clusters of sensitive hair cells. When water pressure changes around the fish, these cells bend slightly, translating the movement into signals that travel directly to the nervous system. Through this mechanism, a fish can detect the presence of another animal even when no light reveals its shape. A distant swimmer produces gentle waves that spread through the water column. As those waves reach the lateral line, the fish senses both the direction and the strength of the disturbance. The pattern of vibrations becomes a map of nearby motion. The advantage of such perception becomes clear in environments where visibility remains limited. A predator drifting through dark water may detect the subtle wake of a passing organism long before it could see the animal itself. By adjusting its movement toward the source of the disturbance, the hunter increases the chance of intercepting prey that would otherwise pass unnoticed. Prey species also rely on the same system. A faint vibration traveling through the water may signal the approach of a larger predator. By interpreting the direction and rhythm of these pressure waves, the animal gains time to alter its course or retreat towards safer territory. Beyond fish, other deep-sea creatures possess structures that perform similar functions. Some crustaceans carry fine sensory hairs along their limbs and antennae. These hairs bend in response to passing water currents, allowing the animal to detect nearby movement with remarkable sensitivity. Even gelatinous organisms may respond to vibrations transmitted through their soft tissues. Sound travels through water as well, often over long distances. Certain deep-sea animals produce low-frequency noises by moving specialized body parts or vibrating internal structures. These sounds spread outward in expanding waves, sometimes serving as signals between individuals or as tools for locating prey. For large predators, acoustic perception becomes particularly valuable. The movement of a fish, squid, or crustacean can create complex patterns of vibration in the surrounding water. Experienced hunters learn to interpret these patterns, distinguishing between the steady motion of harmless drift and the purposeful swimming of potential prey. The water column therefore becomes filled with subtle traces of activity. Every tail movement, fin stroke, or shifting body sends new vibrations outward. To animals equipped with sensitive receptors, these disturbances reveal the presence of life, even when direct observation remains impossible. In the deep ocean, this sensory awareness shapes how animals move through their environment. A predator may remain nearly motionless while listening to the faint signals traveling through the water. Prey animals adjust their swimming patterns to minimize disturbance, attempting to pass quietly through areas where hunters might be waiting. These interactions occur constantly, yet remain invisible to observers who rely primarily on sight. Beneath the darkness, a network of vibrations connects animals across the water, carrying information through currents and pressure waves. Through lateral line systems, sensitive hairs, and the perception of sound, deep-sea creatures navigate a world where movement itself becomes a signal. Each ripple in the water contains meaning, guiding predators toward opportunity and alerting prey to the presence of danger long before either animal comes into view. Time moves differently in the deep ocean. In regions far below the surface, the pace of life often slows to a quiet rhythm shaped by scarcity and distance. Animals drift through enormous spaces where encounters remain uncertain, and much of existence unfolds in extended periods of stillness. Many deep-sea creatures spend long stretches suspended within the water column, their bodies carried gently by faint currents. Instead of constant swimming, they allow the surrounding water to guide their movement. Small adjustments of fins or tentacles maintain orientation, yet these motions remain subtle and economical. Each movement consumes energy, and in a place where food appears unpredictably, energy must be guarded carefully. This slow rhythm reflects the conditions that define the deep ocean. The arrival of nourishment from distant waters above does not follow regular patterns. Organic material sinks gradually through the depths, dispersed across wide areas before reaching animals below. Because of this, predators cannot rely on frequent feeding opportunities. Many species survive by conserving strength during long intervals between meals. The bodies of these animals reveal adaptations suited to such restraint. Muscles often remain thin yet efficient, designed for brief bursts of action rather than sustained effort. Some species possess buoyant tissues that reduce the need for constant swimming, allowing them to remain suspended in the water with minimal movement. Others rest quietly near the seafloor, blending with the surrounding terrain while waiting for activity nearby. Even the metabolism of deep-sea organisms reflects this slower pace. Chemical reactions within their cells proceed gradually, allowing energy to be used over extended periods. Digestion itself may take many hours or days, particularly after a large meal. Through this reduced metabolic rate, animals stretch the value of each feeding event. Because life proceeds at such a measured tempo, sudden changes stand out sharply against the background of stillness. A faint vibration traveling through the water may signal that another animal has entered the vicinity. Currents shift slightly as a body passes nearby, altering the delicate balance that surrounded the drifting predator moments earlier. In these rare moments, the quiet rhythm of the deep sea can transform quickly. A hunter that remained motionless for long intervals may respond instantly when prey approaches. Muscles engage with sudden precision, and the predator moves forward in a brief burst of acceleration. Such attacks appear abrupt not because the predator is restless, but because it has waited patiently for the right opportunity. The energy required for a strike is saved carefully during the long periods of inactivity that precede it. When the moment arrives, that stored energy releases in a single, decisive movement. For prey animals, the same pattern shapes survival strategies. Many species drift cautiously through the water, minimizing disturbances that might reveal their presence. Their movements remain smooth and controlled, designed to pass quietly through areas where predators may be waiting. Even small adjustments of direction occur gradually, preserving the calm environment around them. This balance between stillness and sudden action defines the deep sea's rhythm. Long intervals of drifting fill the majority of time, punctuated by brief encounters that unfold quickly and often without witnesses. The animals that inhabit these depths have adapted to this pattern, conserving strength until the rare moment when movement becomes necessary. Within the vast darkness, the ocean continues its slow pulse. Currents drift, organisms glide quietly through the water, and energy flows through the ecosystem at a deliberate pace. When two paths finally intersect, the calm surface of this rhythm breaks for an instant before settling once more into silence. Human presence in the deep ocean remains brief and uncommon. Most of the world beneath several thousand meters of water continues its quiet existence without interruption from observers above. When exploration does occur, it arrives slowly, carried downward inside vessels built to endure the immense weight of the surrounding sea. Submersibles designed for deep exploration resemble small moving capsules descending through darkness. Thick walls of reinforced metal and specialized materials protect the occupants within, while powerful lights project narrow beams outward into the water. As the vehicle sinks deeper, the familiar blue of the surface ocean fades until the view outside the window becomes entirely black. Inside the craft, scientists watch the landscape of the deep ocean unfold gradually. The seafloor appears first as a distant shadow, then resolves into plains of sediment, scattered rocks, and occasional ridges rising from the bottom. Each descent brings the possibility of observing animals rarely seen in their natural surroundings. Remotely operated vehicles extend this exploration even further. Connected to research ships by long cables, these machines move along the seafloor with precise control from operators above. Cameras mounted on the vehicle transmit continuous video, allowing scientists to examine the environment in detail while remaining safely on the surface. Despite these technological advances, the portion of the deep ocean explored by humans remains extremely small. Each expedition can observe only limited areas during a dive that may last several hours. Outside the narrow path traced by a submersible or robotic vehicle, vast regions continue without direct observation. When researchers encounter animals during these dives, the moments often pass quietly. A fish glides across the field of view, its movements slow and deliberate. A drifting organism pulses gently through the water column before disappearing again into darkness. These encounters provide valuable insight into how deep-sea species behave in their natural environment. Occasionally, a submersible records something more dramatic. A predator may appear holding recently captured prey, or two animals may interact briefly within the glow of the vehicle's lights. Such observations offer rare glimpses of the feeding relationships that shape life at these depths. Yet, even these scenes remain incomplete, revealing only fragments of interactions that occur throughout the surrounding ocean. Most predator encounters likely unfold far from the presence of research vehicles. The enormous scale of the deep sea ensures that many events occur beyond the range of cameras and lights. A hunt may begin and end within seconds in a region where no human instrument happens to be watching. For this reason, much of the deep ocean ecosystem still carries a sense of mystery. Scientists combine the observations gathered during exploration with other forms of evidence, such as collected specimens and environmental measurements. Each piece of information contributes to a gradually expanding understanding of how animals live and interact in these depths. New technology continues to extend the reach of exploration. Improved cameras, autonomous vehicles, and advanced sensors allow researchers to remain longer within deep environments and observe animals with less disturbance. Even so, the scale of the ocean ensures that many behaviors remain difficult to witness directly. Within the darkness below, countless organisms continue their lives largely unseen by human observers. Predators move through the water in search of opportunity. Prey drift cautiously through the same spaces, and the rhythms of the ecosystem unfold quietly across enormous distances. Submersibles and robotic explorers provide windows into this hidden world, yet the view they offer remains partial. Beyond the illuminated circle surrounding each vehicle, the deep ocean stretches outward into silence, carrying within it an intricate network of life that continues far beyond the reach of human sight. Far below the shifting weather and sunlight of the surface ocean lies a wilderness, larger than any desert, forest, or mountain range on land. It spreads across most of the planet, covering immense plains, trenches, slopes, and ridges that remain largely untouched by human presence. Within this silent expanse, life persists in ways shaped by darkness, pressure, and long stretches of emptiness. Across these depths, animals move through water that offers little guidance from light. Vision fades into shadow, and the environment reveals itself through faint signals of movement, vibration, and the occasional pulse of bioluminescent glow. Organisms navigate this quiet terrain using senses refined over millions of years, detecting subtle disturbances that drift through the surrounding sea. Encounters between creatures rarely occur by chance alone. The ocean at these depths is vast, and animals often travel slowly through immense spaces before crossing paths with another living form. When such meetings happen, they carry unusual importance. A single moment of contact may determine whether energy is gained or lost, whether a predator feeds or continues its search through the surrounding darkness. Scarcity shapes nearly every aspect of this world. Nutrients arriving from distant waters above settle gradually through the water column, forming a slow rain of organic material that sustains many species. Larger sources of food appear only occasionally, scattered unpredictably across the seafloor. Each organism has adapted to this irregular supply through patience, efficiency, and careful use of energy. Predators in these environments rarely rely on prolonged chases. Instead, they drift quietly, conserving strength until opportunity arrives within reach. Some wait motionless, while others move with steady, deliberate strokes through the water. Their bodies reveal designs refined by long evolution in a place where unnecessary motion carries a cost. Prey species follow equally careful strategies. Many remain nearly invisible in the dim surroundings, their bodies reflecting little light or blending with the faint glow filtering from above. Others rely on delicate, defensive responses that unfold in seconds, releasing bursts of illumination or altering their posture to confuse approaching hunters. These adaptations together form a delicate balance. Each species occupies a role within a system that functions without the constant abundance found in brighter oceans. Energy moves slowly from one organism to another, linking predators, scavengers, and drifting life into a network that stretches across immense distances. Human knowledge of this realm remains incomplete. Research vessels, submersibles, and remote instruments have revealed remarkable glimpses of its inhabitants, yet the explored portion remains only a fraction of the whole. Vast stretches of seafloor and open water continue without direct observation, quietly supporting ecosystems that unfold beyond human sight. Every new descent into the deep ocean expands the story slightly. A newly recorded species, an unfamiliar behavior, or a previously unseen interaction adds another piece to an enormous puzzle. Scientists continue to map these discoveries carefully, building an understanding that grows gradually with each expedition. Beyond the reach of exploration lights, countless animals continue their slow journeys through darkness. Predators glide through silent water in search of opportunity. Small drifting organisms settle gradually toward the seafloor. Scavengers patrol wide territories where the next meal may arrive weeks or months later. This quiet wilderness remains one of the largest environments on Earth, yet it also stands among the least observed. Its rhythms continue, regardless of human attention, shaped by forces that operate patiently over long stretches of time. Within its darkness, life has found ways to persist, adapt, and endure. The deep ocean invites reflection on how much of the planet remains beyond ordinary view. Beneath the familiar surface lies an immense landscape where survival depends on subtle signals, careful movement, and rare encounters. In this hidden world, the story of life continues quietly, unfolding across a realm that still waits to be fully discovered.